So hello there and welcome to another tutorial. My name is Tanmay and today we're going to be talking about some of the brand new concurrency features introduced to Swift. Now just yesterday at WWDC 2021 when they announced the brand new async await functions and actors to Swift, I was really excited and I just really wanted to delve into these brand new features. I'll be covering actors in a future tutorial. Today I want to focus on async await functions. Before I get into that though, if you do enjoy this kind of content and you want to see more of it, please do make sure to subscribe to the channel as it really does help out a lot, and of course turn on notifications if you'd like to be notified whenever I release new content. Apart from that, if you have any questions, suggestions, or feedback, feel free to leave it down in the comments section below, and I'd love to go ahead and hear what you think or answer any questions you may have. Now, diving right into this, let's start off by talking a little bit about Swift. The Swift language, as you probably know, is Apple's programming language, and it's most popularly known for being the one language that you use for basically everything Apple platforms. So if you're building an iOS app, your go-to is probably going to be Swift. If you're building a macOS app, probably that as well. At least I would hope so. And so, when you build Apple platform applications, you're usually using Swift. But Swift does a lot more around that, right? Swift is open source. It enables you to write applications for Linux and even Windows now. And one of Swift's main design goals has always been safety, which I will say is criminally underrated in the programming world. I feel like a lot of programming beginners don't necessarily realize the full scope of just how much a safe language can help you out and sort of speed up your development process, right? Like, for example, optionals and these sorts of language safety features. A lot of the times, beginners when they're getting into a language will think, this is unnecessary ceremony, right? This wastes time. It makes development slower. Why do we need this? But really, when you start to, boil away all of that ceremony, you realize that when you're developing even medium to, larger scale applications, without those safety features, things can take way more time than they're supposed to, just because you will end up making mistakes in places where you didn't need to, places where the compiler could have caught those mistakes if it had enough information about what you were trying to do. Really, this entire thing is about trying to tell the compiler what you're trying to do so it can catch your errors for you. Right? So Swift takes entire classes of programming errors and effectively translates them to compiler errors instead of runtime ones. Optionals really help you out so you never have those null pointer exceptions. Right? If let, optional chaining, guards, all these sorts of things. Swift's unique exception handling system enables you to have all kinds of really, unique errors, and it's really just a more expressive way of being able to throw errors. And now, Swift safety is coming to the world of concurrency. Concurrency is traditionally, notoriously difficult to do right. And that's just because, the human mind sort of thinks serially. You think doing task A, B, C, D. So having to change your mindset to think about multiple threads doing multiple things at once and somehow syncing and converging and communicating can sometimes be a really difficult thing to do. However, now, with the power of these new Swift features, concurrency is a lot easier. Issues like data races, issues like, blocking threads, these can all be avoided with these brand new features. Now, in particular, let's start off by talking about something not even related to concurrency necessarily, but just related to how computers work. So let's talk about busy waits. Now, as a programmer, you might know what a busy wait is already, but let me just quickly catch you up to speed in case you don't. Let's just say you're running an application on a single core CPU. So the CPU only has a single CPU core, single thread running. So at once, the CPU can only do a single thing. Now, let's just say your application needs to sleep for 1 second. Now, if you were to type into, say, Python, time.sleep1, imagine what would happen if Python said, while true, continue for 1 second. What would happen is your CPU for an entire second would be continuously used doing nothing, just looping until that 1 second is over. That's called a busy wait. It uses your CPU to wait. Now, there are other kinds of waiting. For example, if you were to ask your kernel to help you do a sleep, what would happen is you would tell your kernel, hey, for a second, I don't need to execute this process. And what your kernel can then do is it won't do a busy wait. Instead, It'll take control from your process. You won't be executing anymore for an entire second, but the kernel can still keep other things running in the background. It can context switch out of your process into something potentially important and then move you back into that process after that second is complete. That's, context switching. However, if you're doing a busy wait, then your kernel doesn't know that, hey, wait, this thread is free. We can be doing other things with it. Similarly, imagine you're building a SwiftUI application to search through movies on the Open Movie Database API. Now let's just say you submit a new query for SpongeBob, and you're downloading all of the all of the cover art for all these different movies, all the posters. Well then, these are files, and files, especially images, take time to download. So before you render your UI, or really on the same thread as your UI rendering, if you start downloading all those images, your app has become completely unresponsive. Nobody can do anything on the application while the poster art is downloading, and there's nothing anybody can do about it. But if you launch a new background thread and unblock your UI thread, suddenly people can still interact with your application while it's downloading in the background. But then you've got to write the code to make it so the background thread can communicate with your main thread so that you can get the posters and actually show them on screen. So how do you do that? Well, traditionally, you do it with what's known as a completion handler. So you call a function which is responsible for taking, say, the URL to the poster art, and it will launch a thread in the background. It'll download it, and then you would have also passed that function another function. And when that function is done downloading the poster, it will call that function pointer that you passed and tell that function, hey, we finished getting this image. And effectively what that does is it enables that background thread to communicate back to you that, hey, we finished downloading and here's the image. The issue with this architecture is that just passing a closure to a function in Swift doesn't tell the Swift compiler anything about what you're trying to do. You, as the programmer, understand that passing that function closure is an abstraction, and that abstraction is effectively to make it so you can communicate back from that background thread when it's done to your state to update your UI, for example. But the Swift compiler doesn't know that. As far as it knows, you're just passing another closure. It doesn't know why. And so because of that, it can't enforce a bunch of safety features. For example, if you have a regular function that just returns an integer, then Swift will make sure that all code passed through the function return an integer. There is no way that this function can complete execution without having returned an integer to its caller. Swift can ensure that safety. But with that architecture of passing closures, Swift can't ensure that you call that closure and pass it something that is valid. There's no way for Swift to know to do that because it doesn't know that you're trying to use the closure as a kind of return almost. Right? And so these are the kinds of safety features that you miss out on. However, with this latest version of Swift, all of these problems can be forgotten because now you can use async await functions to replace this whole completion handler architecture. Effectively, what you can do is, let's just say you have a simple function, and what it does is, like the one on screen right now, it loads a movie's plot through a JSON response from the Open Movie Database API. Now, effectively, what this code is doing is it's taking a movie structure, which is also on screen right now, and from that movie structure, it's extracting the IMDb ID, it's passing it to the OMDB API, and it's serializing, or rather deserializing, decoding the JSON response from OMDB into a structure, and then extracts the plot from it and returns the plot. So this is a simple function that gets the plot of a movie. Now, in this specific example, what I've done is I've marked this function async. What does async mean? Well, it means that this function is being called in an asynchronous context, meaning that it's possible for this function to, out of nowhere, suspend its execution and tell the system that, hey, I'm waiting for something to happen, you can do something else right now. So, for example, let's just say we're making our actual URL session a request to get data from a URL. Now, that's something that takes time to go to a URL, fetch something, come back. So we mark that function call with await, because data for and then some URL is an asynchronous function. It's also defined as async. So within this async function, we mark our function call as await. So we're waiting for that function to give us something. Now, when we say await, what we're telling Swift is, hey, load plot is now, at least for now, done executing. Suspend this function. We're not going to continue until we get a response from URL session. But then, once we do get a response, resume execution of this function. So now the system, macOS, knows that, hey, we're not executing this function anymore. Clear up some system resources, go do some other stuff, maybe render the UI or do whatever you need to do on this thread. But then, when URL session does end up returning a response, or maybe a little bit after that, when the kernel thinks it's time, then continue running this specific function. And then, as if it were a synchronous request, you have the result of the actual request as well as the response from the server stored in your variables. No need for a completion handler, no need for a closure. It really is magical. Now here's the thing. Functions that are asynchronous can suspend their execution. If you don't mark a function with async, it can't just suspend out of nowhere. That means that only async functions can call async functions. So for example, if I didn't mark this function as async, I would not be able to call URL session shared data for URL. And the reason for that is because that would be a regular function, which is not allowed to just suspend out of nowhere. And if you're awaiting for that function, then you might end up suspending. And so, you're probably wondering, if only async functions can call those functions, how do you start that call stack? Like, how do you make that first async call and jump the bridge from the synchronous world to the asynchronous world? Well, you can use what's known as an async task. So within your synchronous function, what you can do is effectively just write async and then a curly bracket, and then within that async block, you're allowed to make those calls to asynchronous functions. You're allowed to await for them. That asynchronous block launches a new thread effectively, and so your original function will continue execution after that async block. It will not wait for it to be complete. The async block just goes ahead and starts a new asynchronous sort of thread in the background. So that is how these new async await features work. I have built a little application that I'd love to show you, and it effectively enables you to search through OMDB using this new async await feature in Swift. And then I'd love to go ahead and walk you through the code and how this is possible. So let's go ahead and take a look at it. Let's start off by taking a look at a demo of the application that I've built. Now, if you go ahead and launch this application, as you can see, it's built in Swift UI, so it's able to automatically adapt to, for example, light and dark mode. I'm currently in dark mode. And if I go ahead and search for, let's just say, SpongeBob, and I hit the enter character on the keyboard, then it instantly goes ahead, runs that search against OMDB, and it does this, again, entirely asynchronously in the background. The UI is still responsive as it does this. In the first pass of the API request, all it gets are the movie's titles and years as well as their IMDb IDs. It then stores that internally, and then it goes ahead and launches per each cell in the list. It then launches two new threads essentially, or asynchronous sort of streams of execution. And within these streams of execution, one of them is responsible for downloading the poster, and the other one is responsible for making another API call to get the plot of that movie. So again, there's three sort of, stages to this asynchronous operation. There's number one, which is do the initial search and create the actual movie cells. Then there's actually, display those cells on the screen. And then for each cell, launch two new asynchronous streams of execution, one of which is to get the poster, one of which is to get the plot. Now, as you can see, sometimes you'll see like a little loading icon instead of the poster, and then you'll see the poster. That's what happens if at first the cell doesn't have a poster, but then the asynchronous task is like, oh, hey, here's your poster, and then we display it on screen. But if the asynchronous task throws an exception or an error saying, wait, no, we couldn't get the poster for some reason. Maybe it didn't exist. Maybe it was an incorrect image, something on those lines. Then in that case, we remove the loading little progress or spinner, and instead we just show blank, transparent rectangle effectively. And the plot downloads pretty much instantly because it's just text, but I do that as an asynchronous stream of execution so that that's not blocking anything either. And of course, as you scroll down in the UI, what happens is when the last cell in the list appears, then that triggers a bit of code that's like, oh, you're at the end of the list, and so then it loads in a bunch more next search results, and you can sort of keep scrolling, and it'll detect that you're at the end, and it'll keep downloading more data. And again, for every individual cell that it downloads, each cell gets those two streams of execution that then go ahead and merge back when they're done. So let's go ahead and take a look at the code now. All right, let's dive right into the code. Now, the real magic of this application starts off with the OMDB API class. Now, this code is actually pretty straightforward because, once again, that's the entire point of this. The point of the new async await function features is to make code a lot more intuitive. It's to make it a lot more straight line. So we start off, of course, by defining our OMDB API class. This is what's responsible for actually interacting with the API. I start off by defining an enumeration of the different possible errors that we can encounter by calling the different functions within the API. And then we define the movie structure that you've seen earlier. This has a little bit more detail to it, though. For example, it conforms to the codable protocol. And in order to do so, I need to define another enumeration within it called coding keys. Because this needs to define decodable, or rather conform to codable, because when I actually get responses from OMDB, I want to immediately take that JSON and serialize it into this structure. And these coding keys help me translate the keys that we get from the JSON from OMDB and translate them over to the actual structure over here. I also do have a possible error for getting posters for a movie, which is that we could get an invalid image. And then, of course, we have our 4 fields, the IMDb ID, the title of the movie, the year it was released, as well as the poster URL. And then, of course, we've got our very first async function. Now, if an asynchronous function also throws errors, the async keyword needs to come before the throws keyword in the function signature. This function takes no parameters, and all it does is it returns a UI image. It starts off by trying to convert the poster URL from within its field into an actual URL as a Swift type. If it's able to do so, then it continues as normal. If it's unable to do so, then it throws a specific error, specifically the invalid URL error. Now, assuming everything did go right, then we go ahead and convert that URL to a URL request. Then I go ahead and call another asynchronous function from within this one. This asynchronous function is URL session shared data for request. Now what I'm doing here is I'm awaiting the response from this function, but it can also throw its own error. So the try comes before the await this time. So I'm trying to await a response from this function over here. If this, of course, throws an exception, just like normal Swift, that will recurse up the call stack as this function throws itself as well. Now we will get a result, which is of type data, and a response, which is of type URL response. And then what I can do is attempt to convert that response to an HTTP URL response and attempt to get the status code from that response. Once I do that, I can check if it's equal to 200, which, as we all know, is okay. And if it's not, then we throw an invalid response error. And then, finally, I can go ahead and take that data, which is the response of our URL request, convert that to an image, and if that doesn't work, then we just throw an invalid image error. Otherwise, we can go ahead and return the image. That's all there is to it. Again, the entire point of this is to make writing asynchronous code easy. Now, from there, we've of course got 2 structures, the search API response and ID API response. This is so that I can take the different API responses from OMDB and immediately serialize them to JSON. Because once again, like for example, with the search field, OMDB will return to me JSON, which is a dictionary containing a key, and the value of that key is the array of movies. And so this helps me deserialize that from OMDB. Then, of course, within the actual OMDB API class, I go ahead and define the API key that the user uses to communicate with the API, as well as the last search that was made through the class and the last page that was accessed for a specific query. All I need in the initializer is the API key because we already have default values for these 2 variables. Then, of course, there's my next asynchronous function called search. What this does is it takes an optional query string, like a normal function, which by default I'm setting to nil. Now, what this means is that if there is no query defined, which is the second case for this if-let statement, then I go ahead and take the last query the user made and I rerun that query on the next page of the results. So I continue searching for whatever the user searched for last. However, if I was passed a query, then I go ahead and actually run a brand new search against the OMDB API. Both of these code paths will end up putting a URL in this variable, which we then go ahead and query using the same URL session shared data function. So this logic is effectively the same as what you had seen up here for downloading posters. After that, I do, of course, try and decode the result of the API into my search API response structure, and then I only return the search field, which is an array of movies, as you can see here. After that, there is one more asynchronous function within the API, and it's called plot. Plot takes a movie, and it returns a string. The string is the plot of the movie. It's asynchronous and can throw an error, and is effectively the same as the two functions you've seen before. It tries to convert a string to a URL, after which it tries to make a URL request, and after that request, it goes ahead and takes the response, makes sure it's valid, and then returns the JSON of that response. Specifically, it returns the actual plot string. Now, in order to use this API, I've gone ahead and built a little Swift UI application, and this is the UI code. We start off with our content view structure, in which I create a new API instance, and I define two state variables, which is the search query and the array of movies that we're currently rendering on screen as a list. After that, I've got my body variable. Within the body variable, I simply create a VStack, and this enables me just, to do some UI formatting. I put a bit of a title at the top of the application, and then I put an actual search field. Now, when you click enter on the search field, when you commit on that search field, I go ahead and submit a new query for whatever movie you've typed in, and I go ahead and hide the keyboard with this line of code. Then I've got a very simple list, and this list goes through each of the movies in your array, and for each movie it creates a new movie cell view, passing it the API in the movie that it needs to render, and if this movie appears on screen, if the cell appears on screen, and if the movie it's rendering is the last in the list, then I refresh the movies, I load some new movies in. Now the movie cell view is defined up here. Within the movie cell view, all I really need to define are the API and the movie that I'm trying to render. Now, what I can do from within this movie cell view is I can take a look at the poster. Of course, this is an optional UI image. I can take a look at whether or not the poster was actually loaded successfully, and I can take a look at the plot of the movie. Now, when you actually go ahead and load in one of these movie cell views, then the first thing I do is, of course, within the body, I create a horizontal stack, and that horizontal stack contains the poster, which is defined up here, as well as the movie's title, year, and plot. Now let's go ahead and take a look at the poster logic, since that's very interesting. If we already have a poster and it's not nil, we go ahead and show that poster. If we don't have a poster, and we know that it hasn't failed to load, meaning the poster bad is not true, then we show a progress view, which is that little spinning indicator. But if it's nil and the asynchronous task set poster bad to true, meaning it failed to load, then we just show nothing, a transparent rectangle, making it so that there's nothing there. And of course, showing the title, year, and plot is very simple. However, when this HStack appears on screen for the first time, then we go ahead and load in the actual poster and plot by calling load poster and load plot. Both of these functions need to make a call to an asynchronous function, but these functions themselves are not asynchronous, as you can see over here and over here. And so what I do is I use this asynchronous task feature of Swift to have this brand new block of code effectively. And what this block of code does is it launches in like this new thread in an asynchronous environment where the entire call stack is potentially suspendable. And so you can make calls into asynchronous functions. So for example here, I can try and assign the poster from the movie to self.poster, and if I catch an error, I can set poster bad to true. And here's what's really interesting. What happens is when you run this async block of code, load poster is actually going to return immediately. So load poster here isn't going to wait to load the poster before you load the plot, because async just makes it return instantly. Now, if I were doing something else here, like for example, if I printed async called, async wouldn't make this function return. It would rather go do the print and then return. But the point is that async does not wait for whatever's inside of it to finish before the rest of your function continues to execute. And so, once we go ahead and load in the poster and the plot, we've already got our movie cell view done. Then after that, all that's left within the actual content view is the code for searching for movies, which is very similarly a simple wrapper around that OMDB API class. All it does is it takes the query, which by default we assume to be nil, and if the query is not nil, meaning we're trying to do a new search, we reset the movies that are currently being rendered on screen, and then I go into an asynchronous context and attempt to await for the API to give me a result for that query, and if I do get a result, then I go ahead and add it to my SwiftUI state variable, which contains the movies we're trying to render. And that is how async await functions work. And that's a really simple sample application that helps you actually use these features in Swift yourself. Now, I really do hope you enjoyed this tutorial, and I really do hope it helped you out. Now, if it did, once again, please do make sure to subscribe to the channel. It really does help out a lot. Like the video if you did enjoy it, and turn on notifications so you know when I release videos just like this one today. I can't wait to cover more of the brand new Swift features in some future tutorials. Make sure you stay tuned for that. Once again, any questions or suggestions, feel free to leave it down in the comment section below or reach out to me through social media or my email. I'd love to get in touch. Apart from that, once again, thank you very much for joining in today, and goodbye.